So now we're going to hear from Sam King of UC Davis. He's going to be sharing how the most heavily tested DIY AID algorithm is being made universal across platforms and what that entails. So welcome, Sam.
Thanks, Amy.
Let me get your slides going here.
So today we'll be talking about unified algorithms, and I'll spend most of my time talking about some of our efforts in Trio porting the oref algorithm from JavaScript to Swift. Next slide, please. But just a little bit about me. So in addition to living with type 1 diabetes myself, I'm a computer science professor at UC Davis. I've spent time in academia, startups, and in industry. And from my academic research, if any of you have ever scanned a credit card with the camera on your mobile phone, chances are this was ML and software from my lab. So, spent a lot of time in my research thinking about impact. Next slide, please. All right, I'm going to give everyone about 20 seconds to read this slide. All right, so biohacking. So I remember when I was first introduced to the idea of biohacking, it was probably about 10 years ago. I used to work with a guy who had an RFID tag implanted underneath his skin. Now, an RFID tag is just like basically a small computer system, but he had this implanted underneath his skin. And so he would use it to log into computer systems or unlock doors or whatever people use RFID tags for. And I remember at the time thinking, man, this guy is like the most hardcore biohacker I've ever seen. At least that's what I used to think until I started to learn about type 1 diabetes. So as we all know here, type 1 diabetes, big part of self-management is injecting insulin, and this is done multiple times a day. Now, insulin is a really dangerous hormone, but this is something, decisions that people are making on their own all the time. Some people use computer systems called automated insulin delivery systems to do the injections for them. And, managing type 1 diabetes goes beyond just insulin. So a lot of people will run experiments on themselves and try to understand how the metabolism responds to life. This includes more banal activities like how it responds to when you eat food or exercise, but also more racy activities like how's my metabolism going to respond when I'm having sex or taking recreational drugs. And so once I really started to learn about type 1 diabetes, I came to the conclusion that the guy with the RFID tag underneath his skin, he was actually a rookie. The most hardcore biohackers out there, people living with type 1 diabetes. And so that's who I want to build computer systems for. Next slide, please. So in my research program, I have an intentionally provocative hypothesis where essentially, if you get diagnosed with type 1 diabetes, it comes with some pretty severe, has the potential to come with some pretty severe health consequences. But in my research program, what we're trying to do is trying to convert that. So if you get diagnosed with type 1 diabetes, you're actually expected to live longer than your otherwise healthy peers. Now, there isn't some, magical AI pixie dust that we can sprinkle on the problem and have it all work out. I think it's going to take a lot of long and hard work, but this is our goal. This is what we're aiming towards. Next slide, please. And the first step towards this is really, really nailing algorithms for insulin dosing. So today I'm going to talk about unified algorithms for insulin dosing, and I'll divide it into two broad parts. The first one to give a little bit of intuition and a little bit of motivation. And then I'll explain some of the lessons that we've learned porting Trio's oref algorithm from JavaScript over to Swift. Next slide, please. All right, so shown here on this slide is a chart of glucose data. For those of you who use Night Scout, this will look familiar. So each of the dots represents a CGM reading represented in milligrams per deciliter on the y-axis here. And the numbers overlaid on top are bolus insulin entries, and then the blue lines at the top are the basal rate set on the pump at any given point in time. And so the thing that's really interesting about automated insulin delivery systems is you have an opportunity to take all of this data and essentially run an experiment every 5 minutes. Next slide. So for example, if you look at the data that I have shown here and you see the two regions that I have circled, there's no digestion going on and the glucose levels are relatively flat. You can calculate basal rates based off of this. Next slide, please. Or maybe you see a rise in glucose levels and very likely this is coming from a meal. And so you can calculate how many carbs are likely to be in the meal, how long is it likely to last, and so on. Next slide. One more forward, please. Or after digestion's done, if you see glucose values dropping, you can calculate insulin sensitivity. Next slide. And so having all of this data and this ability to run experimentation really gives you a lot of great opportunities to build a dynamic system. And one system that's out there today that does a very good job at making use of this experimentation framework is the oref algorithm from originally from OpenAPS. So if you look through the literature, there are a couple of papers I want to highlight. One from New England Journal of Medicine says oref is both safe and effective. And there was also an interesting study about using oref in fully closed loop, and the basic conclusion was that like it works pretty well, maybe as well as hybrid closed loop. And so when I look at these papers, and as somebody an algorithms aficionado, the conclusion I draw is from the algorithms that are widely used, I would claim that oref is state of the art. Next slide, please. So to give you a little bit of insight into how oref works, I'm not going to get into too many nitty-gritty details, but I just want to explain, like, to me, the most important concept in the algorithm. And it's this idea of glucose impact. Now, essentially what glucose impact means is if you look at insulin delivery history, you look at the physiological settings, you look at carb announcements, you can take these different settings and you can mathematically calculate how you would expect glucose values to change. So let's say that you have a ton of insulin that's active, no meals that you know about, you would expect glucose to drop. And you can calculate this using some physiological models. And the result is what's essentially a theoretical change in glucose. Next slide, please. And so then what oref does is takes this theoretical change in glucose and compares it to what's actually being measured using a CGM and can look at the difference with something called a glucose deviation. And so the insight here is if your glucose deviation is very high, that means that there's some extra source of glucose that you haven't accounted for. And then likewise, if it's low, that means that you're absorbing more glucose than you're expecting to based off of this theoretical calculation. And so really the difference between the theoretical changes in what you can measure, this is the key insight that underpins a lot of what happens with oref. Next slide, please. And so this kind of basic observation is used in a bunch of different algorithms that are part of the overall algorithm system. There's an algorithm called AutoSense, which will adjust insulin sensitivity, another algorithm called UAM, which is for unannounced meals. It will be used for forecasting future glucose values and so on. Next slide, please. But the problem is that there are a number of different implementations of this same basic algorithm. So OpenAPS was the original one. It's written in JavaScript and still exists today. There's also Android APS, Free APS X, IAPS, and Trio. And each of them have their own variants of oref. As these systems have evolved, they've built in their own features, and sometimes it requires changes to the core algorithm. And so each of these apps are running versions of oref, but they've all been changed in subtle but important ways. Next slide. And so all of these choices in AID systems is great. Like as a user of AID systems myself, I have my own personal preference. I like using Trio, but like depending upon what you're looking for, you have a number of different choices that you can pick. But if you look at it from an algorithmic progress perspective, it becomes really hard. So let's say that somebody takes Chris's new dynamic ISF and they implement it in Android APS. It becomes really hard to then take that and port it into Trio. And the reason is things are different enough that basically you'd have to start from scratch. You can't just take the same concept and move it over. You kind of have to redo things from the beginning. If there's a problem in one of the implementations, it's really hard to tell if it's also present in another implementation. And so although the variety of AIDs is a good thing, I think it's currently we have some work to do from the algorithmic perspective where we can really take advantage of the community and all work together to try to improve the algorithm. Next slide, please. All right, so now I'll get into some of the nitty-gritty details of what we've learned from porting oref from JavaScript to Swift in Trio. Kind of the big takeaway from it is a first step. We really need unified test cases. I know this is not what people want to hear. Literally nobody gets a computer science degree so they can write test cases. But when I look at like the most impactful thing, both in the time I've spent personally working on this and what I think we would be great as a community, as a unified set of test cases would be amazing. Next slide, please. All right, now with our high-level goals for the port, so we wanted to take this JavaScript code base and we wanted to port it to Swift. And so we had two basic goals. And so the first one is because the system is running pretty well and we wanted the ability to confirm that our Swift implementation is correct, we wanted the inputs and the outputs of the two algorithms to be the same. So in other words, if you were to run the JavaScript and the Swift implementation side by side, we would expect them to produce exactly the same results. The second goal is we wanted to use what's called idiomatic Swift. And this is just a fancy way of saying that the Swift code that we use, we want it to look like it was written by, written as a part of Trio or written as an iOS app natively. We didn't want it to look like JavaScript that happened to use Swift context. We wanted to take advantage of the tooling that's available in the platform. Next slide, please. One more. Perfect. So in terms of what went well, one of the things that I think we really did well is we built the ability to replay inputs and figure out what went wrong if we detect that there's an issue. So in the original implementation of Trio, the way it works is there are a bunch of inputs that get created into a JSON object. And JSON is just a way to represent data. So you take this and you feed it into the JavaScript function, and then it'll give you some more JSON, again, a way to represent data, but this is the output. And it can then take that and use it in the rest of the app. Next slide, please. And so what we did is we built a system where we run both a JavaScript implementation of a function and then the equivalent Swift implementation of the same function, and we run them side by side. And what we'll do is compare the results of the two, and if we see any inconsistencies, we'll take the inputs that were used as into these algorithms and we'll log them up into the cloud. Next slide, please. And of the things that we did, one of the things that I'm really happy with is the way we built this was very privacy friendly. So as a first principle from the start, end user privacy was a strong consideration. CGM and insulin data is very sensitive, but we put a lot of time and thought into coming up with a good way where we could enable ourselves to make sure that the algorithm was correct, but at the same time respecting people's privacy. Second is it gave us the ability to actually debug problems. And so, if you think about what's happening is there's somebody who's using a device in Europe and, they get this inconsistency, the system will just log that for us. And then in California, I can replay their inputs and recreate the bug there, the inconsistency that we saw previously, and then fix it, which is just an absolutely amazing capability. You don't have to copy around logs here and there, have conversations with developers. Like this just all happens automatically. In addition to logging the inconsistencies when there's success, we won't log the inputs, but we'll at least keep track of how long did it take the algorithm to run, was it successful, and so on. And then finally, we're building up a database of really interesting corner cases so that when we get a really nasty bug, we'll kind of keep a record of this. And so that way, as we continue to change it and make improvements, we can always go back and replay all of the old logs just to make sure that we didn't make a mistake that broke something else that used to be working. And so in the end, I think our replay system is something that I'm pretty happy with. Next slide. All right, so now for the things that didn't go so well. Next slide, please. So the first one is like seemingly a simple issue where it boils down to how computers represent numbers. And so computers have two main ways to represent numbers. They're different data types called a decimal versus a double. And both of these are used for math, but the fundamental difference is decimal will give you exact values, but it takes a long time to calculate. Doubles will give you approximate values, but it's really, really fast to calculate and has hardware support and very widely supported and so on. And so the JavaScript is using doubles, and then in Trio, we use decimals. And so, for example, if we have some simple math, 0.1 plus 0.2, if you're using decimals, that equals 0.3, kind of what you'd expect. But if you're using a double and you add 0.1 plus 0.2, you get 0.3000004. And if you don't believe me, try it yourself. This is the answer. And so it ends up creating some difficulties. Next slide, please. Now, the first thought of how to deal with this is relatively simple. Like these numbers are close enough, for the purposes of what we're doing, you can just check to see if the two are approximately equal. Next slide, please. Next slide. It turns out that didn't work. All right, next slide. So the problem is in intermediate calculations, you aren't just taking values and passing it through. These values sometimes are part of logic, which controls what code gets executed. So if you see the code snippet that I have listed here on this slide, there's an expression up at the top. If A is less than or equal to 0.3, you do something, otherwise you do something else. Well, in our previous example, the decimal example would have taken a different code branch than the double example, and so they would have executed different code. Even though this value is like almost exactly right, the code they execute ends up being different. And since we're comparing outputs identically, that ends up becoming problematic. Next slide. And so our solution, unfortunately, was painfully manual. So we had to go through the JavaScript and find all the places where these little imprecisions would cause this type of issue, add some precision to it. And we never really found a good automated way to nail it. It just, took some good old fashioned roll up your sleeves and put the time into to find all these little cases. Next slide, please. Now, the second issue was what to do if we found a bug in the original implementation. Now, to be clear, any software running at any level of scale is going to have bugs. This is a fundamental issue. So I'm not trying to poke fun at the original algorithm or anything like that. Like all software that's ever been written at any sufficient size has bugs. And so we had planned for this from the start, and our plan was to take the bugs that existed in the JavaScript implementation, port them over to the Swift implementation, but keep a record of it so that we could go back and make a decision if we wanted to clean things up. But we saw a bunch of cases where sometimes the bugs would have conflicted with some of our other goals. Like maybe, it would have been really hard to express it in a clean way using Swift, or some other cases where there were some calculations that were incorrect. And so we kind of had to face this tough decision of what to do. One of the things that made it really hard is that we believe that some of these issues that we think were bugs, people who use the systems just end up working around it naturally. So even if like from a pure correctness perspective, it's incorrect, like people are kind of using it in a way where they know that, or they don't know, but they implicitly know that it's incorrect and they work around it. And so it kind of leaves us in this really tough decision about how to handle it. And so essentially we ended up taking a two-pronged approach where some bugs we would port from JavaScript over to Swift, and then for others we would test. So next slide, please. And so in our testing framework, once we have these logs that I mentioned previously and we replay them, we have two sets of JavaScript that we run against. One is the original JavaScript that runs inside the Trio app, and then the other is a version of the JavaScript that we fixed. And so now we can compare this fixed JavaScript against Swift. And essentially the way you can think about it is that we're testing out the fixed code ahead of time using the current set of data that we're looking at. Next slide, please. All right, and so the last lesson learned is LLMs aren't really good at AID software. So, originally when I signed up to work on this, I was thinking, oh yeah, this is going to take a month or two. I'm going to throw it into ChatGPT and it'll be done, right? And so, the AI synthesis tools are pretty amazing, but they definitely have some rough edges. Next slide, please. Next slide. So what we found are that these LLMs, when you ask them to do the work, the thing that they did really well, if you think about our goals, they were really good at creating idiomatic Swift code. So they've seen tons of examples of what good Swift code looks like. And you say, hey, ChatGPT, can you port this? And say, sure, let me port it. And it would look really nice. And they did a generally pretty good job. But the problem with it is it would have a number of really subtle but important bugs that it would add. And so we ended up spending more time when we tried this, we ended up spending way more time trying to debug what the LLM had created than if we just ported it manually. And so, I think for the most part, we end up all of the code is hand ported from JavaScript over to Swift because that was the way that we could get the best results in the least amount of time. Now, I will mention that one thing LLMs were amazing for is creating test cases. So, they're extremely good at taking JavaScript test cases and porting those to Swift. And they were also very good. If you have some code, you could ask it to create test cases. Now, it wasn't fully automated. You still had to have a human go through and check everything to make sure it was right. But at least in my experience, it saved a ton of time by using it. Next slide, please. So for people who are interested in working on this in the hackathon, I have a couple ideas that might be interesting. So first, just my own personal strong opinion is that each of the platforms should have their own native implementation. But kind of given that, that means that the unified algorithm will have some challenges, but I still think we can do a lot better than we're doing right now. So the first task would be define a uniform set of inputs and outputs for each of the key functions. So before we can even start talking about testing, just defining like, here's the data that goes into this function and here's what data we expect to return would be a huge step in the right direction. Next one are creating a bunch of test cases. As I joked earlier, no one signs up to do test cases, but like honestly, the amount of time that I spent personally on this, most of it was doing testing. It's like extremely high leverage work. And if you're interested in LLMs, I think it's one of the places where they do pretty well with AID software. Next one is formal verification. So personally, I'm a huge advocate of mathematical proofs of correctness for software. I think it's going to be a hard problem with oref, but it's like very much worth it. So if you're interested in formal verification, it's something I have some experience with. Come chat with me at the hackathon next weekend. I'll be happy to provide some guidance. The next one is a plan for extensibility. So each of the different implementations have their own version, their own features that they support. And this is not a bad thing. This is a good thing. We still need to support that, but it would be great if we could come up with a way of supporting that without having to change the core algorithms. And then the last one is my research lab. We have a lot of experience running ML-based algorithms. I've run an ML-based algorithm personally for some time. And they're like really interesting, but I don't think we're quite there yet. I think there's still some more work to be done. And I think oref can play an extremely important role in that. All right, next slide. And just to be clear, this is not just me by myself. In particular, Dan and I were the two core developers on this feature. All the code that was written was from Dan and I. But this was not just Dan and I in isolation. The whole Trio team helped out with this. And so this was really, really a team effort to get to where we are. I'm just kind of representing the lessons learned. All right, next slide. And that is it.
Hi, Sam. Thank you so much. So when you open that chat window, go to the far right, the tab that says Q&A, and there are definitely some questions posted there.
Gotcha.
Yeah.
So basically setting aside other functionality, looking at Trio and Loop DIY algorithm, This suggests Trio is much superior on Loop DIY. I'm not sure I would go that far. I think everyone's use case, everyone's needs are different. You know, for a lot, I know a lot of people that love Loop and use it. I know a lot of people that use Trio, AAPS, and so I think it would be hard to say that there's a winner, but I have not seen the data from the Pancreas for All paper was pretty compelling in favor of oref, and that's the system I use. Okay. If developers, regardless of ecosystem, follow the same heuristics for the algo, is it still as different? So I guess, do we actually need to agree on a unified heuristic? Um, it kind of depends. Like, I think the more we can agree, the more we can take advantage of other people's efforts. But like, absolutely, you know, there are going to be ways where people implementations will deviate. That's kind of what I meant by the extensibility part, though. I don't think there's a good answer to it. I think it's a hard problem, but that's why it would be interesting for people to look at it at the hackathon. How can we potentially make pump CGM integrations more compatible across architectures in Loop versus Trio? So I think that across the AID systems, I think a lot of them do use LoopKit for pump drivers, and so there should be quite a bit of overlap. I haven't looked at Loop in a while, so I'm not sure if there's an exact overlap, but I think a lot of people use LoopKit as a foundation. On the AAPS side, I don't have a ton of visibility into what's going on there. So next one, so basically setting aside other functionality, looking at, okay. What algorithm does Omnipod 5 AID use? Is it a public or proprietary one? You know, I used to know this at some point. There's a paper that mentions which algorithm they're using, but I don't know. I don't know off the top of my head. But maybe there's someone from Insulet here who could answer. You stated no automated way of testing, but we know to test code before use, like insulin dosing, where accuracy and safety are paramount. Can AI create agents to help test? So, I mean, I think there are a lot of ways to test code. I don't think an AI agent is necessarily what we need. So when I mentioned what I would do is have ChatGPT create unit tests, so just source code, and then I would manually go through and look at it and make sure that everything looked right. And it like saved a ton of time. Like writing unit tests is very tedious and takes a long time, and it just saved a ton of time. But there was still the manual human step of checking that it was all working. I'm not sure if this answered your question, but just to clarify, there wasn't an AI agent involved. Did you make a list of identified bugs in original JS and the fixed done? Yes. So we have it's in the private Trio repo for now, but everything that we found is documented, and we should have that code in the public repo very soon, and we'll pull all the issues over along with it. And we've been communicating with developers from other AIDs as well. So if we saw big ones, we would try to draw consensus. I think Scott even weighed in at one point. Can you say something about how this effort can be taken advantage of by AAPS due to Swift being pretty Apple-centric? Okay, so here's kind of what I mean. I don't think that AAPS has actually already ported oref to Kotlin, which is the native language in Android. So I don't think they would necessarily need to use anything that we did on the Trio side. But this is why I think it's so important that we kind of agree, like, here's a blessed set of test cases, and if you can pass this, then you're like oref compliant or something like that. And I think like that is really where I can see a lot of the sharing happening. Did you include auto tune with Trio? No. So the question is, did we include auto tune with Trio? No, just only auto sense. Trio doesn't use auto tune.
Well, Sam, thank you so much. I'm sure people are going to be excited to connect with you in the in-person hack and also later in the program today. So thanks so much. Yeah, stick around. We'll be talking with you more later.